Hello and welcome to the presentation on iDOT, a dot calculus with object initialization. Our contributions are as follows. We provide a simple intuition behind an initialization system which prevents null pointer exceptions and is suitable for mechanized safety proofs. And we do this in the dependent object types or DOT setting without sidestepping object initialization like previous calculi. So, suppose you're trying to keep track of trees and fruits and you want to keep track of what tree each fruit comes from. So you write some code such as the following. You have some fruits which keep track of their trees. You have some trees which keep track of their fruits. And then you have some code to create these recursive objects. Here we pass mango tree to the fruit constructor and mango to the tree constructor. And then we do some field reads. This looks harmless enough. So we run our code and we get a null pointer exception. What happened here was when we passed mango tree to the fruit constructor, mango tree was not initialized. So what was passed was a null reference. And the fun part is we really do need 3 field reads to get this null pointer exception. So let's fix our code. We modify the tree constructor so that it takes in no inputs and it creates fruit objects with access to the this variable. And it works. We no longer get a null pointer exception. But then we start thinking. We look at our code doing the field reads and we notice that we have an invariant. Fruits always point back to the tree they come from, so reading the tree field of a fruit field should always get us back to the tree itself. But this is not reflected anywhere in our type system. In fact, we could have gotten our code wrong and called the fruit constructor with the wrong tree. We keep thinking and suddenly we have a light bulb moment. This isn't Java, this is Scala. And in Scala we have the types to enforce these kind of invariants. Enter path-dependent types. These are the types we'll use in our program. In Scala, fields of objects can not only carry data or references, but Scala also has fields which contain types. These are called type members. Scala also has intersection typing. Here, the tree field has to be both a tree and an object with a type member f, which has to equal the generic parameter t. In the tree constructor, we use path-dependent types. Here, the type this.f is dependent on the path this, a path of length 1, but in general, we can have longer paths in types. Also, by using the this variable, we get type-level recursion. By using recursion, this.f becomes a type that's unique to individual objects. So the type member f on one tree is different from the member f on another tree. And the fruit field must contain a fruit corresponding to the tree's unique type member. I will now argue that we have enforced the invariant that we set out to do. Suppose m is a tree. If fr is a value of type fruit of m.f, then fr.tree can only point back to m. And this is because from the left of the intersection type on the tree field, fr.tree.f must be m.f. From the right of the intersection, fr.tree must be a tree. And m is the only tree that can have the type member f equals m.f. Therefore, fr.tree has to point to m. This is the code for our actual constructors. Previously, we only showed the types. Most of the magic happens on the last line of tree, where the correct types and variables are passed to the fruit constructor. If we had passed the wrong type to the fruit constructor, we would get a type mismatch error from the fruit constructor. If we had passed the wrong value to the fruit constructor, we would again get a type mismatch error from the fruit constructor. If we had passed both the wrong value and the wrong type to the fruit constructor, this time the fruit constructor would succeed, but we would get a type mismatch error from the tree constructor. So we have encoded our invariants into types and we're happy for now. But we keep thinking again. Are path-dependent types safe? We do some reading and we run into this paper from OOPSLA 2016. Here they show that null pointers can make path-dependent types unsound in Scala. Let's return to our invariant slide. Firstly, I lied earlier. The tree field can not only point to the tree, but it can also be null. But that's relatively harmless. The OOPSLA 16 paper shows that it can be much worse. Suppose we have the following Scala code. First, we have a type unsafe of L with a member A with a lower bound of L and an upper bound of fruit. We then initialize a variable of type unsafe of any with null. There are no objects of the type unsafe of any because any such object would need its type member A to be assigned a type that is both a supertype of any and a subtype of fruit, and no such type exists. However, Scala allows null to be the value of any reference type, so we can assign null to unsafe. Once we have done this, the whole type system falls apart. With unsafe in the typing context, from the bounds we have that fruit is a supertype of unsafe.a, which in turn is a supertype of any. Any is a supertype of all object types. So now, by transitivity, fruit is a supertype of any object type, and we can initialize the fruit variable, which is supposed to have a fruit type corresponding to a unique tree with anything we want. So now we've completely broken our invariant, and the tree field can point to any object it wants to. So we now start to get a little worried. But thankfully, we keep reading and we find out that path-dependent types are safe. In the same year as the Unsound paper, a provably type-safe calculus with path-dependent types were presented at the Wadler-Frisk gathering. You can see the phrase dependent object types, or DOT, here, and shortly we will introduce a new DOT calculus. Since Wadler-Frisk, there have been several DOT calculi, and we can stop worrying about the safety of our code if we can translate our code to an existing DOT calculus. Can we translate our code to any of these? Kind of, but not really. The problems we run into are as follows. Wadler-Frisk DOT has the problem that it has no notion of uninitialized fields. Objects are allocated with fields pre-populated with terms that are lazily evaluated on field reads. Accessing a field behaves like Scala methods introduced using the def keyword, but we were looking for something that behaves like Scala fields introduced using the var or val keyword. Wadler-Frisk has no notion of field mutation, so there's no notion of replacing a null with something more initialized. It also has no constructor, so there's no distinction between code that assumes objects to be initialized and code that's initializing objects. PDOT calculus from last year's OOPSLA also has no notion of uninitialized fields. Fields are always pre-populated with values or paths. It also has no field mutation or constructors. The kappa-dot or k-dot calculus fixes many of these shortcomings. It has constructors and field mutation, although the constructors are first class. But we still don't have a good Scala-like notion of uninitialized fields. Just like Wadler-Frisk, objects are allocated with lazy terms in their fields, but these can be mutated to contain pointers. Fields can be accidentally left lazy, which can lead to runtime divergence on field access. So we decided to fix these. In our paper, we introduced the iota-dot or iDOT calculus. iDOT does feature uninitialized fields where objects start off having null fields which are later mutated with references to objects. Field reads are strict, just like in Scala, so our objects have a very Scala-like feel to them. iDOT has a sound initialization type system which ensures no null pointer exceptions happen. This system is based on a previous system called freedom before commitment. We mechanized the soundness proof for iDOT and it's around 10,000 lines of code. Compare that with k-dot, which is around 6,000 lines of code for its safety proof. So overall, we added around 4,000 lines of code to the safety proof for k-dot. Our overall system consists of three parts: a type system, an object initialization system, and an effect system. The type system, which gives types to terms, is mostly unchanged from k-dot. The initialization system, which gives initialization types to terms, prevents field reads on uninitialized objects. We have two initialization types, free and committed. The effect system, which tracks definite assignment effects of terms, ensures that constructors initialize every field. The initialization system we use is a fragment of freedom before commitment without nullable types. The initialization system classifies objects as either free or committed, where free means the object can have null fields or null fields are reachable from this object. Field reads are not allowed on free objects. Committed means null is not reachable from the object and field reads are allowed on committed objects. We fixed k-dot's fields by modifying constructors so that they allocate objects with null fields. Null are only allowed in fields and we do not allow reading null from fields, and we never substitute variables with null references. Plus, we follow Scala's null typing and allow null fields to have any type. For proving safety, we conceptually split up the heap into two parts: a stack of free subheaps containing objects being initialized and a committed heap containing fully initialized null-free objects. Note that these subheaps are conceptual, there are no runtime costs associated with them, and in reality we have one flat heap. But the splitting helps with our small step safety proof. In this setting, we create a mutually recursive graph of objects by first allocating a new free subheap and then allocating multiple objects on that subheap. Then we are free to set up references between these objects. In the middle of this, we have the flexibility to create a fully initialized set of objects. These new objects can be dependently typed on the previous objects. Once we're done, we can promote the new set of objects to the committed heap. After this, we can continue our setup, but now we can refer to the new fully initialized set of objects. We can also do field reads to reach deeper into the object graph. Once we're done, we can promote the last subheap, and we now have a larger graph of objects which are fully initialized and may be mutually recursive. In the split heap, we have the following points to invariance. Objects in the committed subheap can only point to other committed objects. For objects in free subheaps, they can point to either committed objects or to objects in the same free subheap. We allow the following heap operations. We can add a new free subheap, or we can allocate new uninitialized objects on the topmost free subheap. Once the topmost free subheap becomes null free, we can promote it to become part of the committed heap. We allow the following assignment operations. We can make a committed object point to another committed object. For objects in the topmost free subheap, we can make them point to either committed objects or to objects in the same free subheap. No operations are allowed on other free subheaps. So to make assignments on another free subheap, we have to promote free subheaps on top of it. The initialization system uses both the typing context gamma as well as the initialization context delta, which maps variables to initialization types. We allow writes from the previous slide, but the last two operations should only be allowed on the topmost free subheap. But the typing rules do not really know about subheaps. The way subheaps come into play is by letting delta only have mappings from our objects in the committed subheap or in the topmost free subheap. The scope control through delta happens when we type constructors. For typing the body of the constructor, we remove all pre-existing free mappings from the context before extending the context with initialization types for the parameters. Calling a constructor can allocate a new free subheap. So by removing all existing free mappings from delta, we are removing access to the topmost free subheap, which is no longer topmost. For typing constructor calls, when a constructor is called with only committed arguments or no arguments at all, we assume that the object will be fully initialized and null-free when the constructor returns. We think of the constructor as allocating a new subheap when running the body of the constructor. Here, the constructor has access to only the committed subheap from its arguments. If some of the constructor arguments are free, then null fields may be reachable from the object when it returns. We think of the constructor as allocating objects on the same free subheap. Here, the constructor has access to the existing free subheaps through its arguments. Now let's see how the initialization system plays out in our example. The code starts off by calling the tree constructor to allocate a new subheap with a new uninitialized tree object. Then the tree constructor calls the fruit constructor, passing in the uninitialized tree. This allocates a fruit object in the same free subheap. In the fruit constructor, we make a free-to-free assignment and then return from the constructor. Back in the tree constructor, we make another free-to-free assignment. Now, both the tree and the fruit are fully initialized and null-free, so we can promote the objects to be part of the committed heap. Lastly, we perform several field reads on committed objects. This time, we're truly happy. There are lots more in our paper, such as details about translating to existing DOT and about our type safety proof. We also discuss extensions to the language that make the calculus more usable. Our mechanized proof includes safety proofs for these extensions. Thanks for listening, and I'll see you at the Q&A session.